So thank you very much for joining to these academic training lectures. As you know, okay, before starting the introduction, that there will be first the speaker will deliver the lecture, and then at the end we will have our normal questions. Okay, so you can do it via chat and I will read them, or raise your hand. Today, and following with our outstanding speakers, I'm very pleased to introduce you the fourth speaker, Kent Lindstrom, who is going to talk about optical fiber transmission, how to cram bits into fibers. He has more than 20 years of experience from telecom industry, and he has held various positions at Transmode and Finera, including a 4-year assignment in the US, where he worked as the director of sales engineering. Prior to this, he was also having several positions at Ericsson, and I'm sure that we are going to enjoy a lot this lecture. We are going to learn many things. So please join me to welcome Ken Lindstrom. So now I'm going to share the slides. So please you tell me next slide and I will go, okay? Just some seconds.
Thanks a lot for the introduction, Maria. It's a pleasure and an honor to be a part of this training lecture. Of course, I wish I could have been there in person, but as you all know, that was not possible this year either.
So, is it working well for you?
I can see it properly, so you can change to the next slide. Agenda here. This is always a difficult task to talk in front of a new crowd where I don't really know what kind of knowledge you have, and from what I've understood, you have fairly different knowledge. Some of you are kind of experts in the area, and some of you are more on the beginner side. So I will try to cover this in a fairly high pace, but it's going to be difficult to go into the depth in any of the areas. But I will start with a kind of the basics around wavelength divisioning multiplexing by talking about some of the fiber aspect, the transceiver part of it, and also an introduction to wavelength divisioning multiplexing. Then there are, of course, challenges that you need to overcome in order to shoot a lot of data for long distance. So I will go through some of the challenges around that with fiber loss, fiber dispersion, OSNR, etc. And then some of the modulation formats that can be used to transmit and shoot data long distance over a transmission system. And last but not least, some slides around the optical solutions that you need. You need to take the components that we go through at an earlier state and form them into a solution to shoot data in a way where it's easy to use and say predictable. So that's the agenda. You can jump to the next slide. So one of the fundamental things here is that, of course, if we're going to talk about the fiber optical transmission system, you need a fiber. So what is a fiber? Well, a fiber consists of 3 different parts. If we start from the middle, we have a core. It's basically a piece of glass. The diameter of the core varies depending on what fiber type it is. You have 2 types, multimode and single mode. Single mode is what I'm going to focus on primarily here. Then you have a diameter of 9 micrometer. So that's pretty much the same size as a hair string. So it's a very, say, small medium that you shoot a lot of data into. Around the core, you have something called the cladding. The cladding is kind of an isolating material that prevent the light within the core from, say, disappearing and lose too much of its intensity through the walls. So it's kind of an isolating material for that. And then outside you have the coating. That's the cover for the fiber, because it's very easy to break a fiber if it's naked. And then the coating can be of different sizes as well, depending if it's a patch cord that you use within a data center, or if it's a fiber that you put into the ground, then the coating will be much, much thinner. So that's the kind of basics. If we then compare between multimode and single mode fiber, then we can actually jump to the next slide. So multimode fiber has a, say, bigger core. So that allows the signal to distribute in waves that goes in different paths within the fiber or modes. Typically, multimode fiber, you use wavelengths around the 850 nanometer area. And when the wavelengths are bouncing in different directions and different paths across the fiber, it will be distort along the line. That means it's going to be difficult to, if you send data with a very predictable and 1 and 0 pattern, it's going to be difficult for the receiver on the other side to predict the data if it's been kind of messed up too much. You typically use multimode fiber for interconnections within your data center or within your IT site. So a couple of 100 meters is a typical transmission distance for it. I'm not going to talk anymore about multimode fiber after this. I will focus on single mode fiber, where you have a narrower core so that the light is only traveling in one mode. So it's very predictable how it goes. It minimizes both the distortion, but also the loss of the light. So you can go longer distances and you can have a much more predictable pattern of the light. And you can use some of the, say, the more advanced technologies with coherent modulation and so on in single mode fiber. You can have a transmission distance up to thousands of kilometers, literally, if all optical, if you have the right equipment around it with amplifiers and etc. So from now on, I will focus on single mode fiber. Then we can jump to the next slide. When it comes to transceivers, so in order to shoot light into it, you use a laser. There are different ways of doing this, but I will talk about the pluggable optics, the pluggable transceivers that you can plug in directly into your switch and router. There are numerous of form factors. I showed 3 different types here, but in general, you can say that each new technology comes in a fairly large form factor. And then when the technology gets mature, it has a tendency to shrink, like in many other areas of what we do here on the both telecom side and in many other technology areas. So if we take the top part there, the SFP, SFP+, that is typically what you use for 1 gig and 10 gig transmission today. They used to be much bigger. It was another form factor that was previously very commonly used called XFP, that was bigger than this. Now, no one uses XFPs anymore. On the 100 gig side, QSP28 is the dominant form factor, the one that you see in the middle. The first generation of 100 gig came in the larger form factor that you see at the bottom, the CFP, CP2s. So it's a lot of, as a innovation in order to get to the smaller form factor. And why do you want to get to the smaller form factor? Well, you want the density on the front plate of the switches and routers, so you can get as much data in with the least amount of space consumed. Then if you jump one ahead, Maria, so it's an animation. There are also a lot of different connector types. So the 2 most commonly used in today's systems, if you look at the transceivers, are the LC connectors that you see on top, or the MPO that is used together with some of the multimode technologies. The SC connector, you don't see many transceivers with SC connectors anymore, but it used to be a quite popular and common connector type in the past. There are, of course, other connector types as well. And to make this the matrix even bigger, we can go to the next animation. There are, among each form factor, there are multiple different types as well. So if we take the SFP and SFP+, we have, for example, short range, long range, extended long range optics, where you use different wavelengths to get different transmission distances. So that's on the 10 gig, up to 10 gig. When you go up to 100 gig, you get another complexity to it as well, because then you also, with new types of transceivers, you will also start to use new type of connectors. So it can be a bit of a challenge to select the right type. It all depends on what kind of router you select. Then you have to select the appropriate transceivers that fits into it and works together with that. Then if we jump to the next slide, I will use some terminology here when I talk about some of the capabilities with dB and dBm. So the unit dB and dBm stand for decibel and decibel milliwatt. The absolute power is measured in dB. I know that this is probably something that you're very familiar with, but if we look at the 0 dB, that's the equivalent of 1 milliwatt. And it's a kind of a logarithmic scale here. So if you go up in power to 10 dBm, then you have 10 milliwatts, 20 dBm, and you have 100 milliwatts. So you see the table there to some of the comparisons. So it's simple mathematics to calculate it. So it's a formula to do that. And if we then look at power differences, then the dB value is the difference between two dBm values. If we take an example on top here, I'm not sure if you you cannot see my mouse now, right? Yeah. No, so okay, I will. If we look at the transmit side on the left part, you don't have to use them out there. I will talk through it. The TX power in this example is plus 4 dBm, so that's an absolute value. We shoot the data across the fiber link where we get into the receiver with minus 10 dBm, also an absolute power value. That means we have had a fiber loss of 14 dB. So that's the kind of the difference in the terminology. You can jump to the next slide. So this is more terminology. If we then look at wavelength divisioning multiplexing, you can run different services. In this example, we show some voice data storage and video services that goes between two sites or two sets of equipment. You can use an individual fiber pair to connect it. That's typically what you do within your data center. But if you do this across the data centers with maybe 50 kilometers in between, then you need a lot of fiber pair, and it's going to be very costly. So then that's when the wavelength division multiplexing comes in play. So if you take it one step forward, then what you do is that you use colored optics. You use optical transceivers with a wavelength for each service. So each service gets its individual wavelength component, basically a prisma that adds and drops wavelength. Can you hear me? I got a warning here that my internet is unstable.
At some point we were not, but now we can hear you.
I really apologize for this. This is embarrassing, especially when I want to talk about high data connectivity, and the session is about internet. But probably someone have told you in the earlier session that internet can be unstable from time to time, and that's what we suffer on right now from the office. But
and also today is 1st of April, so don't worry.
Exactly. That's a joke by itself to have the training today. But if we then look at the advantage of this is that with the wavelength divisioning multiplexing, you can utilize one fiber pair and go much longer distances. For just a point-to-point transmission like this, if you have fiber, it might not be that much of an advantage. But if you need to go longer distances and you need to start to amplify the signals, then you would have to amplify each individual signal on the left type of scenario. While if you multiplex them, you can then amplify it with one amplifier the entire spectra and get all wavelengths amplified at one go. So that's the introduction to it. And if we jump to the next slide, there are different types of technologies around wavelength division multiplexing. You have the CWDM or coarse wavelength division multiplexing. That was very commonly used maybe 10 years ago for basically bit rates up to 10 gig. Beyond that, it doesn't scale very well. But it's 20 nanometer channel spacing. You can have up to 18 channels. Most of the system vendors, they avoid the area around 1390, where you have the water peak in normal fiber. So you will have a very high loss in that area. So most of the system uses 16 channels with a gap in the middle for two other wavelengths. And then you have the dense wavelength divisioning multiplexing, where you have a much more narrow channel spacing with 0.8 nanometers. You can get up to 96 wavelengths in that area. That part of the spectra is typically called the C band. And here you can, go 80 kilometer unamplified, 200 kilometer amplified in a point-to-point span, and 1000 plus if you use optical line amplifiers. So all the higher bit rates are only existing and working over PWM for any type of transmission. And you can jump to the next slide. You can also send data on the transmission side, both on fiber pairs and on single fiber. Fiber pair means that you use two strings of fiber going between the two multiplexers. So you add data on one side, you do that with, one wavelength per service. You talk to the other side with the same wavelength. Everything that goes, if I call it left to right, goes over one of the fiber, and everything that goes right to left goes on the other fiber. So you basically have only data transmitting in one direction over each fiber. If you use a fiber pair, a single fiber solution, then you typically use different transmit and receive wavelength. You don't want to use the same wavelength both upstream and downstream, because then you will get an interference between the wavelengths and some non-linear effects that that will cause instability of your network. So then you typically use one wavelength going downstream and one wavelength going upstream. So if you look at these two examples, you still use 8 wavelengths in both cases, but in the fiber pair solution, then you get 8 services out of 8 wavelengths. At the bottom one, you only get 4 services out of 8 wavelengths. So everything related to transmission solutions are on fiber pair, because that's when you do amplification and all of that stuff is done on fiber pair solutions. So then you can jump to the next part. So that was the introduction to the topic. Then if we look at some of the challenges that you will see when you want to shoot data over a system, and something that you need to take into consideration when you both select and design the network, then you can jump to the next slide. First of all, we have the fiber loss. The typical fiber loss of single mode fiber is around 0.25 dB per kilometer. So if we take an example here now, where I have a fiber characteristics, where I have 80 kilometer of fiber, I have 0.25 dB per kilometer loss, and I use the standard G652 fiber. That's standard single mode fiber. I use a transceiver with a launch power that goes between +4 dBm down to -0 dBm. And it has a receiver sensitivity down to -23 dBm, but a saturation of -7. That means if you shoot in a higher power level than -7, it will saturate the receiver and you will not be able to detect the data properly. And if you go below the -23, which is the lower level, then the light level will be so low, so you will not be able to detect the signal properly. And if we now look at the solution like this, and I want to calculate the network margin on this, can I do this with this particular transceiver? Well, if you then just go one more there, Maria, and if we look at the calculation for that, we have 80 kilometer of fiber with 0.25 dB loss per kilometer. That means we're going to have a total fiber loss of 20 dB. We have a transmission budget that goes from 0 dB, because we have to calculate on the worst case value. So we cannot assume that everything goes out with +4, because it's a range there. So we use the lowest level, so 0 dBm, and then we can go all the way down to -23 dBm. That means we have a transmission budget of 23 dB, and that would give us a margin of 3 dB, basically the difference between the budget and the fiber loss. 3 dB would be very sufficient margin that I would be satisfied with. So this is an example of how you do kind of network design and calculate simple passive designs. If we were to put one of those multiplexer, a DWM filter, in between here as well, they will also have an insertion loss that you need to take into consideration and calculate with. So depending on what kind of complexity you have on your network, there are a lot of parameters that you need to take into consideration when you design the network. So then we can jump to the next part there, chromatic dispersion. So the refraction index of the fiber has a wavelength dependency. So wavelengths are not traveling at the same speed. Higher frequencies travel faster than lower frequencies. So if we look at the left part there, we have say fairly nice digital signals going into the fiber. After 80 kilometers of transmission, they will first of all have much lower power level because we've suffered from the loss, but they will also be, say, spread out across because the left part of the peak travels slower than the right part of the peak. And to recognize and detect what is a 0 and 1 on the picture on the right is going to be very difficult. So what do we do in order to compensate for that? So if you go one step forward, well, we can do compensate for this in many different ways. You can do electrical regeneration. A very common way of dealing with especially 10 gig is to do use a dispersion compensation module. That's what I have there on the side. You can also use special fiber for this, but then you will get you will start to suffer from some other issues. And last but not least, you can also do use coherent technology where you use a DSP or a signal processor that actually take this into consideration and can compensate for it. But if we look at what the dispersion compensation module is doing, you have light coming in. It goes through a circulator that direct the light from one source going in through a fiber. That fiber is a very unique and special fiber where they have used a technology that they call fiber grading. Basically, they print a jitter in the fiber that reflects each wavelength at a different distance. That means that the wavelength that travels slowest will be reflected first, and the wavelength, the part of the wavelength that travels fastest will be going a little bit longer distance in that fiber. This is still just a 10-meter fiber with a printed jitter inside. So it's still a short piece of fiber that you go through to get this reflection to say reshape the pulse so it looks like it did when you transmitted a signal. So this is a very effective way to say compensate for the chromatic dispersion. We then another thing that you you can go to the next slide. Another thing that you will have to do if you want to go further is to start to use optical amplifier. Basically, you have a signal power level coming into the optical amplifier, and you amplify it, and it goes out with a higher power level. The amplifier that I point there, the red little triangle, that is kind of a block diagram below showing what an EDFA look like. Erbium doped fiber amplifier. The light is coming in through an isolator just to direct the light. It goes through a WDM coupler, where you couple the light coming in from through the isolator with light that you shoot in through a pump laser at 980 nanometer fiber. You splice in an erbium doped fiber piece there, maybe 10 meter of erbium doped fiber, and then you go through an isolator again. Then you will get the physical, phenomena that happens when you mix those wavelengths over an erbium doped fiber. If I make this super simple, the energy of the photons from the 980 nanometer will then basically transfer over to the wavelengths that you have around 1550 nanometer spectra, the C band. So that's basically what this one is doing. I make this now sound very simple, but that's pretty much what it does. Very commonly used. And if you then jump to the next one there, you can see here that the characteristics of an erbium doped fiber amplifier only works across a very small spectra of the entire transmission area. So you cannot use this for CWDM. You can only use it for DWM over those 96 channels. You also have another DWM band in the L band area that has not really taken off. Very, very few people uses that today because the EDFAs are not working in that area. So EDFA is by far the cheapest and most efficient way of amplifying the wavelengths in the 1550 nanometer area, or the C-band. When you amplify data, that sounds perfect, and you can go as far as you want, right? You would think so, but if you jump to the next slide, what you will see is that when you introduce an amplifier, you will not only amplify the light level of your actual signal, you will actually amplify the entire, the zero level that you see on the bottom, introducing a noise called an ASC noise. And that noise then will cause issues when you go through multiple different stages. If you run the animation here, you will see that we add fiber and we go through another set of amplifiers. After the fiber, you will have a lower power level, a lower noise level. You go through the amplifier. Now you will have a high signal power level again, but you will have the composite of the two noise levels that you got from both the first amplifier and the second amplifier. And if you run that again, OSNR is the ratio between the signal power level and the noise level. And if you run it one more time, you calculate it. It's a logarithmic scale, but basically, if you do it in dBm, you take the signal power level minus the noise power level. How to calculate noise? Basically, there are two parameters that really affect the amount of noise. It's the input power level to the amplifier, and it's the noise figure for the selected amplifier. So you can select amplifier basically with different qualities. So this is something that you need to always take into consideration. There is no good way to clean noise. You can make some tricks to minimize the introduction of noise, but you always have to take this into consideration. When you select your transceiver or your transmission system, you have to check and see what kind of OSNR tolerance it has and compare that to the transmission, say, environment that you have in your network. Then you jump to the next slide. So that's some of the challenges. There are, of course, other things that you need to also deal with when it comes to optical transmission challenges with nonlinear effects, etc. But with only 1 hour, I have to skip some parts here. When it comes to modulation formats, if we go to the next slide, in the past, it was all about NRZ modulated data, non-return to zero, where a laser is, or a transceiver typically works in a way where you have, how should I say, you don't turn off the laser and turn on the laser in order to create a 0 to 1 pattern, because then it takes too long time for the laser to get stable. You always keep the laser on. So if you look at the eye diagram there, the bottom level, that is the light level that represent 0. And then you modulate around that in order to create a 1. So, and if you sample that over a long time, you can see an eye diagram that like you see there on the right side, where the top part of that represent the 1 level and the bottom part represent the 0 level. So you want a clean and nice eye like what you see on the picture here. But basically then you have the amplitude, it's called extinction ratio. If you look at the criteria for a transceiver, then you have the lower part is the 0 level and the top part is the 1 level. And each time slot you have 1 bit representation. And if you jump to the next slide, some example of this is 10 gig DWM transceivers or 10 gig LR4 or LR transceivers. They are all based on non-return to zero modulation. So this used to be the only modulation format up to maybe 10 years ago. Then we started to introduce some new technology. Another modulation format, if you jump to the next slide, is PAM4 modulation, where you have basically, pulse amplitude modulation 4 levels, PAM4, where you have 4 different light levels. You have the bottom part, where you have a representation, and you have of say 0, 0. You have the second from the bottom, which is 0, 1. The second from top, 1, 0, and the top one representing 1, 1. So that means for each bit slot or time slot, you now get 2-bit representation. So you get a bit rate that is twice as high as your baud rate. If you go to the next slide, so an example of technology using this is those 100 gig PAM4 DWM transceivers. They actually use 2 of those PAM4 wavelengths that are then squeezed quite tight together, so they can fit into a normal filter or max Dmax window of 100 gig with 100 gigahertz spacing. So by doing this, we can get a 100 gig DWM signal into a standard filter with good performance. This is actually something that you guys are using to a fairly large volume. You probably have a couple of hundred of those in your network, doing a lot of 100 gig transmission using the PAM4 DWM technology. And then if we take it one step further, we have the Coherent modulation, where we now in the optical industry start to get a little bit closer to the, say, radio technology, where you're probably up in, several thousand ohms today. But we introduced this into the optical industry maybe 10 years ago with quadruple phase shift keying, QPSK here to start with. So you got, 4 symbols per bit, and then at 16 QAM came out maybe 5 years ago, but it's recently been launched in the pluggable formats, which is creating a completely new dynamic on the market for how operators build a network. Jumping to the next one there, we then have an example of one of those, the 400ZR. That's a standard that we have newly introduced. It was driven by the big hyperscale cloud guys that wanted a common, make this kind of a commodity. So the way it works is that you have 8 electrical signals. When you start to get up to the higher bit rates, transceivers with this kind of capability, you start to have a limitation of the number of electrical wires going into it on the electrical side as well. So for that reason, we also need to start to use PAM4 modulation on the electrical signals. So here we use 8 times PAM4 modulated signals, where we have 25 say gigabaud going into the transceiver, and then we convert into the DSP into the higher rates there. But then what we do more specifically, we convert it through one of these optical modules. It's a very advanced DSP sitting inside, then convert it into an optical signal with 16 QAM modulation. So this is it's magic that you manage to get all of this technology into that small form factor with a power consumption less than 20 watts. So if someone would have told me 10 years ago that this would be possible today, I would have said absolutely no way. There's no way that can be achieved. So it's really, really impressive, and this really changes the dynamic on how people build the network. Because I will go through on the next session here some slides around transponders and muxponders. Now you have all the capabilities already built in on the module itself. So it kind of takes away some of the complexity of how you build your network. So then I guess we jump over to that part. How do you build your network? So if you jump to the next slide, we have the optical solution piece. So in order to put an optical solution in place, you need a number of building blocks. So if we then jump to the next slide, I've just shown some of them here, but we need some kind of optical max Dmax unit. In many cases, you want to be able to balance your incoming data by using or select from where you should take your wavelength. So you use a wavelength selective switch or some kind of equalizer functionality. You use optical amplifiers, optical channel monitor, basically a spectrum analyzer that you build into the electronics so you can analyze the optical power level, dispersion compensation modules, variable optical attenuators, transponders, muxponders, and optical channel filters. I will go through how those can work together in a system soon, but those are some of the building blocks that we use in order to form a solution. You can jump to the next part there. So this is an example of how to combine those components on a higher level. You can to form a line system using optical multiplexers together with amplifiers, for example, in order to bridge longer distances. You can run the wavelengths directly from the routers with colored optics, like the top shows there, typically referred to as IP over DWDM. You can use transponders in the middle, where you have a gray interface in the router, typically a 1310 nanometer and 815 nanometer optics going into a transponder, where you convert that into some kind of a wavelength with typically some added value. I'll come back to that here shortly, and take that into the filter. Or a muxponder, where you have multiple services going into the muxponder, and you do TDM multiplexing, and then on the optical side, you go out with a higher bit rate, where you have been able to multiplex all the incoming clients into a higher rate. You can run that with your line system. So you can use the different components to form a solution. How you select to do it depends a little bit on, or is different from customer to customer, I would say. But in order to do, a more integrated design from the line system, I will actually show you a picture of what we do, so you will understand on the control loop and the level of software that is necessary to form a good system solution. So if you jump to the next slide, this is an explanation of what the box that you are using for your transmission with smart optics, the DCP-M platform, where we have 40 channel DWDM channels with high level of automation. And what do I mean by that? Well, if we start on the left side, we have a transceiver. In this particular picture is a PAM4 100 gig DWDM. We take this wavelength, we go into the mux. If we look at the bottom left part there with the blue wavelength, for example, we go into the mux with a specific wavelength. We multiplex that through, if I call it a standard multiplexer using a technology called AWG. We go through a block that we call an optical equalizer. That is effectively a component where we get access to each individual wavelength, so we can individually attenuate them to the appropriate level. Then we go through a booster amplifier. In that booster amplifier, we have a monitor port. We connect that to a channel monitor, so a spectrum analyzer looking at the spectrum. We can look at the optical spectrum and then determine what kind of modulation format that is transmitted from the transceiver. We cannot see everything, but we can see if it's NRZ modulated, PAM4 modulated, or Coherent modulated. And then we can use that information to balance the outgoing signals from the amplifier to the appropriate level. Typically, you do this by balancing all the wavelengths to the same level. But you can, like we do in this box, balance them unevenly on purpose by setting up a control loop where you attenuate each individual wavelength in the equalizer and looking at the OCM that we achieve the wanted power. And in this particular case now, we want the PAM4 to have a higher power level than the others going into the line fiber, because they do require that for their optical performance. So that means everything we add on the client side will be automatically detected and automatically balanced to the appropriate level. On the line side, when we connect the box, put on the power to it, we will start to shoot out 15 nanometer CWM wavelength over this OSC optical surveillance channel part, where we go into a CWM filter, shoot that over to the other side where we terminate it. When we then have established connection on this 1510 nanometer wavelength that sits outside of the amplifier, we initiate a delay measurement where we use with layer 2 functionality. With that delay measurement, we will then be able to determine the exact fiber distance. We can do this with like plus minus 200 meter granularity or accuracy. We can then use that information to set a tunable dispersion compensation that we have in the mid stage of the amplifier sitting on the preamplifier side on the right bottom side. And then there we also have it connected to the optical channel monitor, so we can analyze and see what kind of power level that goes out of the amplifier. And we can use a control loop on the line side to set the VOA on the line, so we get the appropriate power level into the or receiver in this case then after the DMAX. So basically what this means is that in a box like this, and I mean, of course, from other vendors as well, when they build a solution around it, it allows you to get automation on the client side when you add new wavelengths. You also get automation on the line side that it adapts to different conditions on added fiber loss, etc. So this is a typical solution using the optical component to make it useful, basically. Otherwise, it would be quite complex to operate and run a network with those components if you try to build a discrete solution around it. And if we look at the other side, next slide, in order to go, longer distances or add some value, you can use transponders and maxponders. Transponders is typically, say, a 1-to-1 ratio. You have one client signal that you then that goes in that you then transmit on one line. So it's a coupled together. The ASIC, the FPGA that sits there, it's typically it typically adds some kind of value. So the client signal will be a standard client signal that you have on your switch and router, a 10 gig Ethernet or 100 gig Ethernet or 16 gig fiber channel. Then in order to shoot that at longer distances, you probably want to add some forward error correction to it. You might want to add some overhead so you can introduce, say, in-band management capabilities, etc. So then the FPGA introduces that by adding a framing. It's typically an OTN framing. There are other flavors as well, but it's a very common way of adding capability onto the line side. And this it will also, of course, convert it into DWM wavelengths typically. And then, of course, you can get, say, significantly improved performance by having the forward error correction to it. So if you want to shoot it, like I mentioned before, you can go several thousand kilometers. You need a very sophisticated forward error correction algorithm there to allow that, together with optimized amplifiers and so on. So this is a typical explanation of a transponder. And then I think this is actually my last slide, a maxponder. It's quite similar to a transponder, but what it does as well is that it converts multiple different clients into a line. So you typically have much lower rate on the clients. So you do TDM multiplexing, time division multiplexing on the client signals first, and then you also add the transmission framing, like the OTN frame, on top of it. So in this case now I show 4, but this could be, for example, 4 times 100 gig on the client side into a 400 gig line where you've also added a forward error correction on the line. So that's a very common combination that you will see on the market here from many suppliers. So that's a very, very quick crash course in, if I call it, transmission and optical solutions. I think I've seen some questions popping up. I think it's probably good. Yeah.
Okay, maybe. Okay, so then, so this is the last one, okay, and then the thank you. Okay,
yeah.
So I'm going to stop sharing, and then I will start with the questions in the chat, unless I can see some raised hands still not popping up. So from Barnabas, how do transceivers handle the handshake to calculate the transmission power? Do they try multiple different power modes until the receiving end approves or confirms that the signal has arrived?
If you look at the latest and greatest in the industry, yes. So when it comes to the coherent modulation formats, then the optics are capable of changing, adapting to modulation formats depending on transmission capabilities. Typically, the transceivers themselves are not able to do that yet. The host system where you plug them in needs to add that functionality. So, for example, if we use one of our Transponders that can do on a 400 gig line side, it can do 300 gig as well if the distance is not good enough. Then we need to add that intelligence into our Transponder. It's not done in the transceiver. If you go just one step back, transceivers before Coherent, they were only, I shouldn't say that, but primarily designed for one line rate and one line rate only. So then they could not do any adaptation. Either they worked or not, they did not work. It was more binary.
Okay, and following with Barnabas again, would the use of a switch router clean up the noise that is introduced by the amplifiers? Would underwater fiber lines require any signal cleaning to be able to reach the other side of the ocean without signal degradation?
I guess it was kind of two questions, right? So yes. the router part there, to, if I call it clean the signal, that's if I call it a typical optical electrical regeneration, that will absolutely remove the noise. So that's a very good way of doing it. However, you need, especially if you go up on the higher bit rates, the transceivers are the most expensive part of the network. So you don't want to do any optical electrical regeneration per service, because you have to do it per wavelength if you don't have to. So, but it's a good way of doing it. So for the, I say, if I call it submarine solutions, if you go from coast to coast, from US to Europe, then you will end up at the landing station and you will barely make that transmission. So there you will have no room to continue optical. So I would say in all the transatlantic solutions, you need to do an optical regen as soon as you hit the landing station on either side. So you don't have any room to continue from New York to Chicago all optical. You have to regenerate the signal in New York if you want to go to Frankfurt. Same thing there. If that lands in somewhere in the UK, you have to then regenerate it in UK as well to get down to Frankfurt. I think that was the answer to the question, if I understood correctly.
Yes, I think so. I don't know if Barnabas would like to say something. I see him connected.
Yeah. That definitely answered my question. Thank you. And I had one more question. So you mentioned that you need some amplifiers, but where is the power coming from for the amplifiers that are underwater cables? Is it like a parallel copper line that's running by the fiber line?
Yeah. Okay. So they are. They are. It's not going to be one small tiny fiber there. So it's it's a fairly big thing. You also have say amplifiers that, like you said, that are powered. You have other technologies in there as well on the fiber itself. So using say passive doped fiber that sits somewhere out on the fiber that enhances the performance of the transmission along the fiber as well. So they use very sophisticated technologies in order to get the highest possible bit rate for long distances. But it's a big cable. You also need all the big steel wires to avoid anchors and so on from breaking the fiber. That's very costly once that happens.
Right, and also sharks.
Exactly.
Okay, so from Barnabas we are done. So, and then I can just see just a couple of comments. So from James, I believe undersea cables have repeaters every few kilometers. I guess using a switch router will also act sort of like a repeater and also clean it up a bit. And then from Fritz, I think he was...
In underwater cables, typically amplification is about every 80 kilometers. But if you would use standard EDFAs, you would still introduce too much noise. So then you start to use Raman amplifiers and other amplification technologies that minimize the noise, but then causes some other complexities that doesn't really comply to underwater cables because you don't have any splices or ODFs or patch panels. But but about every 80 kilometers, the say optimized distance in underwater cables.
Okay, thanks. And then, yes, there was one comment regarding the meaning of QAM. I don't know if you read the.
I didn't read. I kind of I'm not surprised. Once we get into the coherent part there, it becomes quite complicated, and I just made it very, very simplified to talk more about the optics rather than the meaning of the modulation part and so on. So on purpose, whatever summary that made it simplify things basically. I mean, I kind of expected to get very detailed question about coherent modulators and so on. I think for some of you guys are probably really interested in that, probably know 100 times more than I do on the nitty-gritty details of it. So I kind of stayed away from it deliberately and simplified it.
Fair enough. So, okay. So then I don't see more questions in the chat and no raised hands. So I think we are done and finally on time. So it's incredible, but we managed very well. Again, many thanks for
I had to speed it up a bit since I lost the 10 minutes there in the beginning. I do apologize for that once again.
Oh, I mean, finally it went very well. Thank you very much to you and for this fantastic lecture. So thanks all of you for attending these lectures, and today is the end of this series. So thank you very much for this, and I hope you enjoy all this series. Let you know that I'm going to add the presentations as well, from Kent as well in the Indico page. Plus, this is recorded, so also you can see it afterwards. So thank you very much. Ciao, ciao. Have a very nice day.
Thank you.
A long weekend. Thank you. Bye.